Let's do a worked problem on surface area. Here's the problem, 169. We want to compute the surface area of the orange shaded surface. The surface is produced by revolving y equals radical x, the portion of the curve from x equal 1 to x equal 4, rotating it about the x-axis. You can open up OpenStax section 2.4 and look at example 2.21. It's worked in the book. Also in the book, you can reference theorem 2.6 for the integral form of the surface area of a surface of revolution. It's given here. Let's copy that down. I'll use notation SA for surface area. 2 pi, I like to bring that out into the front, and then the rest of it is copied over. F of x is the function for which we are revolving its graph, and that's occurring over the interval a to b. And then the radical in the differential is a length differential. Good. Let's set it up. Recopied over the statement of the problem. We have the graph y equals radical x. Here I've sketched it in yellow. That I want to consider the portion occurring between points 1, 1, 1, 1, and 4, 2, 4, 2, the blue dot. I want to revolve about the x-axis. I've denoted that with this circular red arrow. The x-axis, again, in this picture, is the orange dashed line. Nice. We can note that our bounds of integration on x are going to be from 1 to 4. Pick an arbitrary x between those bounds and look how far a point on the graph being revolved is from the axis of rotation. That distance is radical x. That will be our f of x. That is the radius. Go ahead and look at the formula and plug in the information that we have. A is 1, b is 4, and the function f of x is y equals radical x is radical x. Copy the rest. Nice. Now what we need to do is figure out this term, the f prime term. And we're going to do some computations to figure out how to swap out this entire radical term. We'll begin by noting that y is f. Y is given as radical x. Radical x is the same thing as x to the 1/2. Taking a derivative of x to the 1/2, we get 1/2 on x to the negative 1/2. Next, we need to square that. 1/2 squared goes to 1/4, and x to the negative 1/2 goes to x to the negative 1. To form up the radicand, we need a 1. Rewriting 1 as 4x over 4x, we're able to combine these two terms as a single term. And then finally, we'll need the radical. Apply the radical on either side of this equation. And then now this form is what we can swap out the entire radical with. Let's go ahead and do that. So swapping out with this form here results in this integral. And this particular problem is cooked up rather nicely. In other words, we're getting a nice cancellation with 2 and 2, but more importantly, we're getting cancellation of rad x and rad x. This is a cooked up example. All right, after the simplification, here is our simplified integrand. Pausing for a second, how are we going to evaluate this? Well, thankfully, the radicand is linear. And we can do a simple u substitution with u equaling the radicand. That results in a differential du as 4 times the original differential. Solving for the original differential will cost us a 1/4. Plugging in the old lower bound of 1, 4 plus 1 is 5. The old upper bound, 16 plus 1 is 17. This is an elementary integral in U. Evaluating, we come up with this antiderivative, and then plugging in bounds. Note that 2 over 4 goes to 1/2, and 2 times 3 makes 6. 17 raised to the 3/2. Well, 17 to the 1/2 is radical of 17, and then 17 squared. And then take the radical of that, results in 17. So this is 17 to the 3/2. Nice. That was a worked problem on surface area.